So that's done. Okay. So maybe if people are still joining, so they can join. So I'll request everyone to keep their audio and video off for this session so that we can save some bandwidth. I'll turn off my video in a couple of minutes, so that I'm just keeping my face there. So you know who is conducting the session. Please let me know if I get disconnected or if you can't hear me. And yeah, so since I've already started the recording, let's begin. So this course is on FDTD models with Telegraphers equation. So I've already conducted a course earlier which was based on Maxwell's equations. So this is like a spin-off for that course. And so there are two important terms over here. One is the FDTD, which is the finite difference time domain method, which we'll discuss about in the next class. Then there is the second term is the Telegraphers equations, which we'll discuss in this class. So the Telegraphers equations are basically the a couple of equations which we use for modeling of transmission lines. And this course is being offered as a requirement for me for my Prime Minister's Research Fellowship. So let's talk about me first. So yeah, maybe okay. How do I get rid of this? Yeah, that's gone. Okay. So that's me. Maybe I should use a pointer to show where I am. So this is me. Um, so I'm Anand Kumar. You can refer to me as Anand, and I'm a Prime Minister's Research Fellow in the Department of Electrical Communication Engineering at the Indian Institute of Science, which is in Bangalore. And I'm a visiting student at the Tyndall National Institute in University College Cork in Ireland. About my background, so I completed my bachelor's of technology, BTech, in electronics and communication engineering with honors from the Indian Institute of Technology in School of Mines, Dhanbad. And I primarily work on space-time varying metamaterials. I use computational electromagnetics, and I work on non-reciprocal systems. So that's about me. And so most of you must already be familiar with Microsoft Teams. So this is how the interface looks like, at least to me. Um, so there is this chat option over here. So you can click over here. The chat window will appear on your right hand side, and you can post in your questions there. People will give you the idea of who are the participants in this meeting. There is a raise hand button, so you can press that, and this will notify me if you like you're raising a hand, and you can then unmute yourself and ask question, or like if you have written something in chat and I'm not responding, then you can raise hand. And so feel free to interrupt me and ask questions. Then here are the camera and mic buttons. I'll recommend keeping your camera off for to not utilize a lot of bandwidth, because most of us are like short on data usually, and high speed data is a problem. Um, there's a mic button, so you can unmute yourself to ask questions. I'll recommend keeping it on mute so that we don't disturb the class. Okay, so that's about the platform we are using. You can ask any questions if you have about Microsoft Teams. I hope everybody is already familiar with Teams. Okay, so let's discuss the course outline. So the course outline was shared with during the registration form. There was this pamphlet which had outlined what we'll be covering. So briefly, we'll start with the review of transmission line theory and the telegrapher's equation. So we'll cover this in this class. Then next class we'll begin with an introduction to the computational electromagnetics, and mostly focused around the finite difference time domain method. Uh, so these two classes will probably not see codes. Uh, the third class will start with the modeling of lossy and lossless transmission lines. So the theory about this we'll discuss somewhat in this class, and then we'll begin with coding from here, modeling of lossy and lossless transmission lines. Just a heads up, we'll be using MATLAB. So if you know a bit or two about coding, you can translate your MATLAB codes to Python and C and whatever language you prefer. So the algorithm will remain same. It's just that I find MATLAB to be very convenient. Then once we have modeled lossy and lossless transmission lines, we'll see how do we calculate the S parameters of in this particular scenario, and then we'll see how we model lumped components on transmission lines. We'll discuss resistor, capacitor, inductor, and if they are in series or in shunt on the transmission line. And if we have time left, we'll see modeling of composite right-left-hand transmission lines. So we'll see if we can reach over here. This will be our aim. Okay, so this is the course outline. Any questions on this? Okay, so I guess this was pretty much straightforward and clear. Okay, so why this course? Maybe I'll just turn off my video now. Yeah, so why this course? These are the reasons which I could figure out why you could do this course. There could be a lot more reasons. Uh, so if you want to get started with computational electromagnetics, specifically finite difference time domain method, so this is the course. We'll kind of start from scratch. I'll help you write codes. I'll show how the codes work, simulate them with you, share the results. I'll also share the codes after every assignment, and whatever we discuss in the class will be the codes which I share will be in MATLAB. I hope you guys have access to MATLABs, or you know how to convert MATLAB code to Python, and then Python is open source. The second reason could be you are already familiar with computational electromagnetics and other techniques, for example, method of moments or finite element method, and and you want to know about the finite difference time domain method, or you just want to revise the FDTD and you want to sit through the class so that you can brush up because you have not used it recently. So the other reason could be you want to understand working of EM simulators. So most simulators right now are frequency domain method based on frequency domain methods. And we'll be discussing about a time domain method, but you'll still get an idea how things work in the background. And if you're a bachelor's or a master's student, this course will help you do an amazing BTech or master's project. As far as I'm aware, computational electromagnetics is still scarce among bachelor's students. So, if you do this course, you'll know enough so that you can write good projects and replicate good papers from literature. Now, why to study computational electromagnetics? That's a big question. So, Maxwell's equations are complex. So they're just four equations, but they are complex. And uh, for textbook problems, they are very simplified. We assume a lot of things and then we solve the questions. But for realistic problems, your structure could be very complex, and solving them on pen and paper will not be easy. Uh, so hence we develop solvers and simulators, which are based on computational electromagnetics. So we take the help of computers, which can solve bigger matrices, more complex equations in a shorter time. And hence their computational electromagnetics comes in, and we use them to solve different problems. And the applications could be modeling of antennas, very popular. We use CST or HFSS. They are based on computational electromagnetic solvers. We want to study the effects of electromagnetic waves on tissues for medical diagnosis, electromagnetic packaging, electronic packaging, for a lot, many other things, with radars and imaging, surveillance. So for all these things, we can use computational electromagnetics. Now, presence of the EM simulation. So the computational electromagnetics can be broadly categorized into four parts. So maybe I can shift to a pen. So this is computational electromagnetics, and you can either solve them uh, in frequency domain or in time domain. And the Maxwell's equations can be written in either their integral form or their differential form. And you can either solve the integral form in frequency domain or time domain, and also solve the differential form in frequency domain or time domain. So hence you end up with these four combinations: the integral equations in frequency domain, integral equations in time domain, differential equations in frequency domain, and differential equations in time domain. So these are the broad categories of how we write the computational electromagnetic solvers. And now each of these method can be either done in 1D, 2D, 3D, and sometimes 2.5D. So 1D, 2D, and 3D, you get it. So for example, if it's a transmission problem, it's a 1D problem. If you're trying to solve electromagnetic problem on a sheet, it's a 2D problem. If you're trying to solve it on a 3D antenna, for example, let's draw horn over here. So if you're trying to solve it for a horn, so this is a 3D problem. Now 2.5D is the case when you try to solve it for a 3D problem, for example, a PCB, it has traces and stuff. Uh, but you know that the across the thickness, it's basically the same thing. It's a 2D sheet which has a thickness. So that kind of comes around. We can use a 2.5D technique where we just add a dimension, and there is no great variations in this and all of the thickness. So that's a 2.5D problem. So we will not bother about these things in this course. We'll just look at the 1D problem, which is for a 2-wire transmission line. Now, I've listed some examples of the solvers. For example, EFI, CFI, FECO. These are some 3D full wave solvers based on the frequency domain method. And now quasi-static is when there is we consider uh, there is not much time variation of time, so we kind of assume that uh, the structure does not change with time. So ANSYS Q3D is one of the solvers, which is a quasi-static solver, 3D solver based on frequency domain. ADS, momentum, and AWR are 2.5D solvers. So you must remember they kind of do PCB things. Now there is ANSYS Q2D, which uses RLGC values, and this is a 2D solver in frequency domain. In time domain, TDI is the method for 3D, which is a 3D method based on time domain using partial differential equations. Based on integral equations, and so this is time domain integral equations. And now in FEM is a frequency domain partial differential equations 3D solver. So ANSYS HFS is very popular uh, among antenna engineers and others. Uh, this is a very popular solver, and this is based on finite element method, which is a full wave solver in 3D. And this course we will discussing about FDTD, which can be 3D, 2D, 1D, based on how you write the code. So ANSYS numerical and CST, which is based on FIT, which is a close relative of FDTD, uh, are these examples of simulators, which are full wave simulators based on 3D and are based on time domain partial differential equations. So does anyone have any questions? I hear some noise. Okay, maybe not. So any questions so far? So this is our course. So computational electromagnetics, partial differential equations, time domain, not 3D, 1D, full wave, and yeah, FDTD. So maybe I'll stop over here if you have any questions regarding this. Otherwise, there's a question. Yes, Anil.
Yeah, actually here you said that answer HF is a full wave simulator. So
Yeah,
what exactly this full wave means?
full wave means, okay. So full wave means you'll be solving the Maxwell's equations in time domain with all its variations. Quasi-static is the opposite of the full wave, where there is where we consider that the variation with time in the solver is like we assume that the solver is okay. The structure has a const. Maybe I should give you a better answer. Just give me a second. Yeah. So I just was searching for the definition for static. So if the process is very small, that is your structure is not changing with time. So that is the uh, wave distribution across the your structure is constant. That is a quasi-static case. And if there is if your wave is propagating through the structure, so for example wave propagation is occurring through the structure, that is a full wave simulation. So if your process is very slow, that is your wave is moving slowly throughout the structure. For example, the problem like a charge distribution on a plate, you can just solve it using quasi-statics because the charge is distributed. But if there is current flowing through the structure, that will come inside a full wave problem.
Okay,
Mm,
means can we consider this thing for this slow wave propagation with the dielectric substrate where
Um,
and
I could not follow you. Can you repeat or rephrase your question?
yeah, I'm saying actually according to your explanation what you have given that quasi-static mean criteria can be applied for the charge distribution, but
Yeah.
whereas if current is getting flowing, then we can apply full wave.
Yeah,
So
that's a very simplified, like an example of how.
okay. Okay, fine, thank you. Well,
Okay, maybe I'll give a better answer to this in the next class. I'll look upon it. But this was a very simplistic example that, for example, a plate with just distributed charge is an example of quasi-static problem. But if you have a complex structure which has, for example, antenna propagating, and so in that case, you will have currents flowing throughout the structure. There will be fields radiating that will fall inside a full wave problem.
yeah, thank you.
Okay. Okay, so we'll proceed. Uh, So that was quite a basic introduction to the course. We'll look more about it, the computational electromagnetics and its introduction in the next class. Um, let's quickly look at the references. I hope I have included those are over here. Okay, maybe. Okay, so the Pozar is missing over here. Okay, DM Pozar. So this particular class will be using DM Pozar. There could be alternative books you can look up to, but yeah. So DM Podzar and David K. Cheng, Field Wave Electromagnetics. This is another book which we'll refer to. Computational Electromagnetics with MATLAB by Matthew Nasadiku. So some introduction from this. David B. Davidson is what we'll use in the next class. This book is very important. Um,
Hello.
and then
Uh,
yes,
yes. Sorry to disturb you, sir. Sir, these books can you share it? Do you have these ebooks? If you can share it, it will be great help.
Okay.
Like I was
So
searching for this Matthew and Sadiku computational electromagnetics with MATLAB. I was unable to find this book. So if you
okay,
have ebook,
yeah, I'll see. I think I have them. So I'll share this.
okay. Like if you some of these books, if you can share, not all. Like this, I want this Sadiku computational electromagnetics with MATLAB.
Yeah, yeah, sure. I'll share them with
Thank you
everyone.
so much.
Yeah. So yeah, this is a good book. But this book refers to like multiple methods, and so we'll look for some introduction from Sadiku. Uh, the first few chapters from Davidson are very important for this course. So this book is a must kind for this course. The previous course which I offered was based on DM Sullivan's electromagnetic simulation using FDTD method. So this, I think, yeah, this is the book. So this is a very good book if you want to study FDTD using electric and magnetic field. So this is based on Maxwell's equations, all the problems in this book. The very good book. We'll use this book, but if you follow this course, you will be able to understand everything in this book as well. And so after a couple of classes, we'll actually switch to research papers, which I will share with the during the classes. Some papers will be by TP Montoya. So Montoya's work will be used, and rest will be by my some of my papers as well. So I'll write my name as well. So I'll use TP Montoya's papers, and I have used them to write my own papers. I'll discuss them as well. Okay, so these are the references. Some important information about the class. So I'll keep this slide in almost all the classes. So class timings are although 3 to 5, but so we might reschedule a lot. I'll just let you know before every class. Hence, class recordings will be made available for each class. Oh, just maybe. I'm sorry. Yep, sorry about that. Okay, so we'll probably reschedule a lot of classes. Okay, I'll just let you know. So we won't have the class on 29th. I'll not bother you guys on the Christmas and New Year Eves. Um, Maybe the next class will be in 2024. The meeting link is over here, so we'll use the same meeting link. I hope everybody is added to the Teams group. Please let me know in the WhatsApp group. I hope everybody is again in the WhatsApp group as well, because most information in the last moment will be shared in the WhatsApp group. Here's the QR for the group. There's a course website as well. I'll update it timely. Um, the ISSS portal has not been shared with me yet. I hope it will be up in some time. The admin asked me to start the classes and keep the recordings with me. I'll upload the material in the ISSS portal, the WhatsApp group, and the course website, which is on my website. I'll try to send all the information via mail as well, but keep a look at the WhatsApp group as well. This is my email ID, and during the course, I will give take-home assignments. So I'll just share the solutions as well, but I'll encourage self-evaluation. You need not return the assignments to me. So assignments won't be evaluated. If you have doubts, you can reach out to me either in WhatsApp group, email, or during the class as well. So that is some useful information about the class logistics. Um, so I'll just pause over here and let you think of any questions you might have about the class logistics. Like if you have any problems or concerns, you can ask them now. And meanwhile, if you are not added to the WhatsApp group, please scan it and join. Okay, so I guess this was clear. I will proceed then. So we'll start with the class now, review of transmission line theory and the telegraphers equations. So, yeah. So we'll begin with the lumped element circuit model for the transmission line. So the key difference between the circuit theory and transmission line theory is the electrical size. Now, circuit analysis assumes that the physical dimensions of the components or network are very small. For example, this is a transmission line and your lumped component would be very small. And if a wave is propagating, you will see the phase variation across the transmission line. But for the same wave across the lumped component, the phase variation might be negligible. Hence, and this is a and this is decided by the electrical size, which is based upon the frequency or the wavelength of the wave you are considering. Hence, we consider transmission lines as distributed parameter network, and lumped components are considered lumped components because they are like in the ordinary circuit analysis, there is no phase change across the component. So this is the main difference between these two methods, and yeah, so voltage and current will vary appreciably across the transmission line network. But to solve the transmission line, we will consider a lumped element circuit model for the transmission line, so that we can apply KVL and KCL across the network. Now, this is a two-wire representation of a two-wire transmission line where IZT and VZT are the voltage and current across the Z direction where the transmission line is lying and with time. And this is a small incremental section which is of length delta Z. Now, for this particular circuit, we can write its equivalent in this form, where we have the self-inductance of these two lines given by the series inductor L delta Z. And since these two conductors are in close proximity, we have the shunt capacitance over here. And since these two lines might have finite conductivity, we have this R resistance over here, and this two lines might be lying in some dielectric which might have some loss. So we have G over here. So we have the RLGC components over here, and this is the equivalent circuit, and this will act as our bread and butter for the throughout the course. Now, these RLGC components are all distributed parameters. So their units, instead for example, this resistance is not ohms. This will be ohm per meter. Similarly, inductance is Henry per meter. The conductance is Siemens per meter, and capacitance is farad per meter. You have to keep in mind that the units for RLGC are per meter, and then we are multiplying them with delta Z. So this entire thing will now have the unit ohm. This will have unit Henry. This will again have unit ohm. This that together they will have the unit ohm, and capacitance will have the farad. You have to keep in mind while reading the parameters. Now, if we apply the Kirchhoff's voltage law across the circuit, so then we have voltages on this node as VZT, and then subtracting the voltage drop across this resistor and this inductor will reach to this node, and its voltage over here is VZ plus delta ZT. So writing it down, we get this equation over here. Similarly, if we do Kirchhoff's current law at this node over here, the current IZT is over here, and then current flowing through this branch, current flowing this branch are given over here, and this the current through this branch is IZ plus delta ZT. So we get the two equations from the Kirchhoff's voltage law and current law. Now, if we divide these two equations by delta Z and take the limit Z tends to 0, because we are considering this section transmission line section to be very small, such that the phase variation across this section becomes negligible. So we take the limit z tends to 0, we end up with the differential equations. This set of two differential equations, where voltage is given uh, the RLGC values. So these are the Telegraphers equations. So we have introduced the Telegraphers equations. Maybe I'll pause over here. Let you, if you want to work it out, these two equations, you can go through the circuit, and if you have questions, you can ask. Okay, so now we have introduced the Telegraphers equations. We'll proceed. And you can, as you can see, these are the time domain form of the transmission line equations. And for sinusoidal steady state, we can rewrite this di by dt as g omega I and dv by dt as g omega v. So if you remember your Laplace and Fourier transforms, they basically give you an idea of how to switch from here to here. I see a hand. Yes, Ankit. Ankit, you can unmute yourself and ask question or write it in chat. Ankit, can you hear me? I see your hand is up. Okay. So maybe you can write your question in chat and I'll come back to it. Okay. So for the sinusoidal steady state, we can change it. We can move from here to here. And let's look at the wave propagation of transmission line. So if you solve these two equations simultaneously, we'll end up with the wave equations on the transmission line. So all you need to do is substitute the value of Vz over here, solve it, you'll end up with the second equation over here. And if you put the value of Iz over here, you will end up with this equation over here. So it's pretty straightforward. Maybe you want to work it out if you don't recall it. And these are the wave propagation, the equations for the wave propagation on transmission line. Now over here, we are this gamma, which is the complex propagation constant given. We write it as alpha plus j beta, and which is given by this term over here. So alpha is the attenuation constant, and beta is the propagation constant. And you can see this complex propagation constant is a function of the RLGC values and the frequency. Now the solution for these wave equations are given over here. Ankit, I still see your hand, and if you have question, you can write it in chat. Okay. So the traveling wave solutions. So this is a math problem exactly. So maybe you can refer to a math textbook how we come from here to here. So, but these are this is how we get solution to this equation over here. These two equations. Now, once we have the solution for the traveling wave, um, I'll just read it out that this minus gamma z term represents the forward propagating wave, and the gamma z terms represents the backward propagating waves. Backward is in the sense minus the direction and the plus the direction. So this actually means that if you have a transmission line, you will the wave will propagating in either of these directions, and this basically sums up that. So we got the equations for the wave propagation, its solution, and the expression for the complex wave propagation constant. Now, using this equation from the Telegraphers equation and the solution of the wave, we can use them. Um, we just substitute it over here, and then you can write also write the current in terms of the voltage, forward and backward traveling voltage terms. Now, if you compare this with this term, we can define the characteristic impedance Z naught as R plus j omega L by gamma, and then substitute the gamma from here to here. You will get the expression for uh, the characteristic impedance in terms of the RLGC components and the frequency terms. Now, if we can also compare these two terms and write give this relationship of the forward traveling voltage and current terms. The ratio is same as the characteristic impedance, and which is equals to negative of the for backward traveling voltage and current terms. Also, the wavelength on the line is given by 2 pi by beta, and the phase velocity is given by omega by beta, which is also lambda. So this is some basic stuff. So that's about it for the lambda element circuit model. Now we'll look at the lossless condition for the transmission line. So when we introduced the circuit, we had said that R and G terms basically represent loss. So if we get rid of them, we get the lossless circuit for the lossless transmission line. So the simplest diagram will look like this. So this is how the equivalent circuit of the lossless transmission line will look like. We'll have L delta Z term and C delta Z term. That's it. And why do we do this? So usually the losses are very small, and if you want to reduce the computational complexity, we just get rid of some stuff and see how the device works, and then we can include the losses and see how much difference is there. So in fact, most practical cases, the losses are very small, and we can neglect them and perform our analysis. And to do that, we just get rid of this R and G terms. And for the wave propagation constant, if we get rid of R and G terms, this turns out to be G omega LC, very small. We can easily remember this. And since this is imaginary, the attenuation constant becomes 0. And similarly for the characteristics impedance, we set R and G terms 0. These will cancel out, and this will turn out to be root over L by C. Easy to remember. Yeah, so this is all about the lossless transmission line. Maybe if you have questions, I'll pause over here, let you absorb this. So I might be moving a little bit too quick because we want to just revise the basics. I hope these fall under the prerequisites for this course. Going into them in detail will take a lot of time for this very short course. I hope everybody knows this, or if you don't, there's sufficient gap from this class to the next class. You can refer to textbooks, go through them, work out some problems, so that you can get an idea of the lambda element circuit model for the transmission lines, because that is what we'll be using for writing our codes. And as I said in the beginning of class, DM Codes is the book which I am referring to. It's a very good textbook. It has problems and things written in every detail. So all the text, figures, everything is from Podzar. If I remember correctly, it's Microwave Engineering, name of the textbook. Microwave Engineering by DM Podzar. Okay, so this is the lossless transmission line, and the lossy one just has R and G components. So up till now we have discussed about the transmission line. Now and that to an incremental section and its lump model. Now and we derived the expression for voltage and current across the transmission line. Now what happens if this transmission line is now terminated with a load? So we have the expression for voltage and current across the transmission line from the wave solution to the wave equations. And now this is terminated by load ZL, and the voltage across this is VL, and the current across the load is IL. The transmission line has a characteristic impedance Z0 and propagation constant beta. This is lossless, so there is no alpha, and VZ and IZ are the voltage and current values at any point on the transmission line. The load is located at Z equals to 0, and we move towards the negative direction of Z, and any location is represented by L. Now, the total voltage and current at the load are related by the load impedance. So, at Z equals to 0, we can write this. So V by I at 0 position, and we substitute 0 over here, we end up with this expression. So this is the load impedance relationship with the characteristic impedance in terms of forward and backward voltages. And we can again reshuffle this to get this expression where V naught minus is given in terms of V naught plus and the ZL and Z naught values. And so reflection coefficient can be defined from this expression over here. So this is the definition for voltage reflection coefficient: the amplitude of the reflected voltage normalized to the amplitude of the incident voltage. So this is the incident voltage, this is the reflected voltage, and their ratio is given as gamma, the reflection coefficient, voltage reflection coefficient, and this is given by ZL minus Z naught by ZL plus Z naught. So this is an important expression. We must remember this. And similarly, the voltage and current on transmission line can be written using gamma over here. So what we have done is we have substituted uh, this V naught minus um, from here. Okay, so this we substituted this gamma term from this term. Yeah, so we removed V naught and put gamma and V naught plus over here. So this is the expression for voltage and current through the transmission line. Maybe I'll pause over here just in case you want to go through the equations. Let me know if you have any questions on this. Okay, so we'll proceed. So this is the expression for voltage and current we got in terms of the incident voltage, the reflection coefficient, and the expression for reflection coefficient in terms of incident and reflected voltages, and the load impedance and the characteristics impedance. From these equations, it is seen that the voltage and current on the line consists of superposition of the incident and the reflected waves. So as you can see over here, voltage is a combination of the incident voltage and the reflected voltage, and this is called as standing waves. Now, if gamma becomes zero, okay, so this term becomes zero, it means that there is no reflected wave. And to get the gamma equals to 0, we must have ZL equals to Z naught. So if the load impedance becomes equal to the characteristics impedance, we will have no reflections from here. So all the wave will pass through this. All the wave will be dissipated across the load impedance, and there will be no reflected wave. And this, for this particular case, we call the ZL load to be matched. So a lot of cases you must hear in different labs talking about matched load. So that, which is usually what they call a 50 ohm load as matched load. So this is because the most transmission lines that we have available to us are have the characteristic impedance of 50 ohms, and then we use a matched load, which is a 50 ohm load, to terminate the transmission line, so that we don't have reflected waves at the particular port. Next, if we write the expression for power across the transmission line, which is given by the this expression, real half of real value of Vz Iz conjugate, and then we substitute Vz from here, Iz from here, we end up with this big expression, and taking out common stuff and rewrite, expanding this. So if you notice these two terms are of the form A minus A conjugate, and mathematics tells us that this is equals to 2j or imaginary of A. And since this entire thing is imaginary and we are applying a real function on this, this will get rid of these things. So once we remove the real function, this goes away, and the simplified results gives us the average power across the transmission line is square by Z naught 1 minus gamma square. So if you look closely, this expression is basically tells us this is a combination of the incident voltage, which is this term, and the reflected voltage, which is this term multiplied by the gamma. Uh, the incident power is V naught plus square by 2 Z naught. So this is the incident power, and the reflected power is V naught square. So this should be plus over here, V naught plus square mod of V naught plus square into gamma square divided by 2 Z naught. So this is the reflected power, and the total power is basically uh, incident power minus reflected power. So these are the equations we have derived as of yet. Now, if gamma becomes 0, that is, in that case, okay, so this becomes 0, the maximum power will be delivered to the load, because there will be no reflections and all the power will transmitted to the load. And this will happen when ZL becomes equals to Z naught. And all this is considered when there is no reflection from the generator. So so we are seeing that wave is incident, right? So we must have a source over here, and we have to make sure that all the power which is incident from the source travels to the load. So there is no reflection happening over here. And if there is no reflection over here and we have Z naught equals to ZL, all the power will be delivered to the load. And if this gamma is not equals to 0, then some of the waves will be reflected back, and we call it as return loss because some of the waves is returned back towards the generator, and this return loss is then defined as negative 20 log mod of gamma, which is the voltage reflection coefficient, and this is usually given in dB. So this is the definition for return loss. Maybe I'll pause over here again. If you have questions on this, else we'll move forward.
Sir, will you share the slides?
Yes, yeah, so sorry, I forgot to mention this. So the slides will be shared, the class recordings will be shared, the assignments will also be shared. Most likely the solutions to assignments will also be shared. Codes will be discussed in class. We'll run the I'll try to make a recording of how the wave propagates from the when we run the code. That will be shown in class. The codes will also be shared after the class, so everything will be distributed, uh, and these will be distributed through my website, the WhatsApp group, and hopefully when the IEEE portal comes online. Meanwhile, if there is any delay, I've already told you that all these things are from Podzar. I guess the second chapter. Any more questions? Okay, so we wrote down the expression for voltage and current in terms of the incident voltage, the characteristic impedance, and the reflection coefficient. And then we had also given the expression for the voltage reflection coefficient in terms of the load impedance and the characteristic impedance. We derived the expression for power across the transmission lines. We have now derived the expression for the return loss. Yeah. Moving forward, so in two cases, what happens if the reflection coefficient is zero and what happens if it is one? So if reflection coefficient is zero, that is we have matched load over here. It means there will be no reflected power and hence the return loss will be infinite. Um, and if the reflection coefficient is one, that is all the incident power is reflected back. In that case, the return loss will be 0 dB. It means all the incident power is reflected. So these two are important things. Usually when you read the questions, maybe or text, you have to understand, and maybe you can also write this as negative uh, infinite. Okay. Now, if the load is matched to the transmission line, then we have gamma equals to 0 and the magnitude of the voltage on the line will become constant. And okay, so yeah, so if you just substitute gamma equals to 0, this we are left with just this term, and this is for all z. So it means that voltage throughout this transmission line will be constant, and there will be just change in phase. So and this kind of transmission line is said to be flat. Just normal terminology. You probably won't come across this much often, uh, depending upon which area you work in. So, but good to know. And if the load is mismatched, that is, we have this gamma not equals to 0 in such cases, there will be presence of incident wave and the reflected wave. And in that case, the magnitude of voltage on the line will not be constant. And so we can try to write that. The voltage expression is given over here, and let's just take a mod on this. Uh, this is the reflection coefficient and the exponent terms. Yeah. So we have this L over here, which represents the positive value, and this is towards the negative Z axis. So this the positive distress measured from 0. The load is at 0, and the phase of the reflection coefficient is given by e power j theta. Substituting this over here, we get this expression. So you have to focus on this term. And maybe I'll just start this again. So we have the voltage expression over here. We have put mod 1 plus gamma and the phase term for the voltage. Now we are substituting the reflection coefficients, real and the magnitude and phase part over here, and then solve the terms on the argument. So this is what we get. So this, if you notice, this particular thing says that there is variation in phase throughout the transmission line. So we have a constant magnitude over here, and the voltage magnitude oscillates with position z across the line. So if you move across this line, your L value will change. If your L value will change, this function will give you different values, and this will again change the value of this term, and then this will add and subtract to this V naught plus term. So basically, there is this V naught plus value somewhere, and then your voltage throughout the transmission line will oscillate across this. And based on the this argument value, this could be if this is this maximum value that you can achieve from this is 1, in that case you get the V max value, which will be 1 plus gamma, and this can the minimum value will be minus 1, and which will give you 1 minus gamma. So this will reach a maximum value of V max, and this will reach a minimum value of V min, and your voltage across the transmission line will oscillate between these two values. So, and since there are incident wave and then reflected wave, we have sort of standing wave situation happening through the transmission line, and the maximum and minimum voltages are given to us, and we can define what we call a standing wave ratio, which is a ratio of the Vmax by Vmin, and Vmax and Vmin are given by these expressions. So this is an important expression for us. So, and this standing ratio gives us the measure of the mismatch of the line. Uh, so what do we mean by this? So the standing ratio can vary from 1 to infinite, and when it is equals to 1, this means it is a matched load. So this will become 1 if there is the reflection coefficient becomes 0. So if the voltage reflection coefficient is 0, SWR is 1, it means the load is matched. And if it is deflection coefficient is 1, that is all the wave is being reflected back. This will, the denominator will tend to infinite. So this will give the tell us if it is if it is towards the infinity, it means that it is more mismatched. So whenever we try to design any antenna, for example, we try to keep the Vs voltage standing wave ratio near 1. We try to keep it near 1, and usually the acceptable value is 2. If it is below 2, we consider it to be matched. And if it is above 2, we tend to say that it is not matched well at the port. So that is what we mean when we try to make VSWR near 1. Now the distance between two successive voltage maxima or minima is given by lambda by 2. So if you take this term equated equal to 2 pi, you will get the periodicity, which gives us as lambda by 2, and the distance between maximum and minimum, maxima and minima is lambda by 4. And you can also write the generalized reflection coefficient. That so up till now we were talking about the reflection coefficient at z equal to 0 near the load. You can now, since we have the expression for voltage at any point on the transmission line, we can use that, and we know that this particular ratio is at this point over here, so we can write it as gamma at 0 times uh, the variation through the transmission line. So this is the expression for the generalized reflection coefficient. You don't need to remember this. It's good to know. You can easily derive this while solving questions. Okay, so maybe I'll pause over here if you have any questions to. Uh, Otherwise, we'll next to a few more slides before we end this class. Okay, so we'll proceed then. So we had derived the expression for voltage throughout the transmission line through the transmission line, and the expression for power through the transmission line. We had got the expression for voltage and current, the reflection coefficient, the standing wave ratio, and the generalized reflection coefficient. Now, the real power flow on on a line is constant for lossless line, but the voltage amplitude, at least for the mismatched line, is oscillatory. So this means that we had seen for a lossless transmission line, the power throughout the transmission line will remain constant. But if there is mismatch over here, that is your gamma is not equals to 0, you will have standing waves forming over here, and hence there will be voltage at different points. There will be different voltages, and hence uh, what will happen is the input impedance seen from different points will be different. So Z in one will not be equal to Z in two if you see at different points. So let's solve for that. So for example, at solving for any distance L equals to minus Z from load, the input impedance will be given as the ratio of voltage and current at that particular location. For example, if I'm looking at this location over here, this is L, which is equals to minus Z. And the voltage value and current value, we can take its ratio, substitute these values from here. Let's just substitute it from here and try to evaluate this. We'll end up with something looking like this in terms of the characteristic impedance, the reflection coefficient, and look the propagation constant, and the position of where we are trying to find out the input impedance. So this is what we derived in the previous slide. And now if we substitute the value of the reflection coefficient from here, uh, we have to, and we try to evaluate it, we'll end up with something which looks like this. So we have just substituted the reflection coefficient over here. And once you have done that, you can club values for ZL and Z naught, and the E power, so if I remember correctly, E JX minus E minus JX, or the terms like these evaluate to sine or cos. So you can look up on the internet for the values. So this plus minus values will give you sine and cos. So you'll end up with something like this, and then you can just divide it by cos and get the stand terms over here. So this is the transmission line impedance equations, very popular for solving questions. So this is important equations. I'll recommend you remember this if you are appearing for GATE and other exams. Well, pause over here, let you go through the steps, and then we'll proceed to the next slide. Okay, so proceeding to the next slide. I'll recommend working this out with pen and paper. Now the special cases for the ZL. So up till now we had a load arbitrary load impedance. Now the special cases would be what happens if it is open circuit, short circuit, or if or if this particular length of the transmission line becomes 90 degrees. So we'll look at those now. So if it is terminated by a short circuit, the load impedance will become ZL equals to 0. And we substitute 0 over here, we'll get the reflection coefficient as -1. That means all the power will be, all the waves will be reflected back. Um, the standing wave ratio will become infinite. Yes, if you substitute -1 inside this mod, this will become 0, and This will become infinite, entire thing. Now the voltage and current on the lines, if you substitute uh, yeah, so if you substitute the value of gamma as -1, these terms will vanish, and this can be again evaluated to sine and cos. So you get the expression for voltage and current, the standing ratio. So again, for the input impedance, uh, if you make ZL as 0, this will evaluate to this term tan beta L, and now we can plot these values. Yeah. So the voltage will vary some in this fashion. The current will vary in a cosinusoidal way, and the input impedance will vary with as tangent. So it will move from infinite to positive infinite to negative infinite, taking all the values with the periodicity of lambda by 2. Okay, so this is the case for the short circuited transmission line. Transmission lines. What happens if the transmission line is open circuited? In a similar way, we get the reflection coefficient as 1. The standing ratio becomes infinite. The voltage and currents are against cos and sine, and the input impedance is now a function of chord. So again, if we try to plot them, this will vary as a cos, this will vary as sine, this will vary as chord, taking all the values from negative in j infinity to positive j infinity is the periodicity of lambda by 2. So these all plots are available in Posar with detailed explanations. I'm just brushing over them. Give it a read. Now, ignore this for now. So, taking the special case of when the length of the transmission line, for example, we were right now looking at this was a transmission line, and then there was this loading impedance over here, and we were focused on the load. But what happens if this length of this transmission line becomes lambda by 2? If this becomes lambda by 2, irrespective of ZL and Z0, the stand terms will go away, and we end up with input impedance equals to the load impedance. So if we are looking from over here, if this is the point we are looking at the input impedance, whatever this Z0 be, the input impedance will translate to the load impedance. This is what happens if it is lambda by 2, and so this is true for half wavelength line or any multiple of lambda by 2. This does whatever be the characteristic impedance, it will not alter the input impedance over here. Now, similarly, if this becomes lambda by 4 or its multiples, the expression will evaluate to something like this: Zn equals to Z0 square by ZL. We call this as quarter wave transformer, and this is frequently used for in matching two transmission lines. So this is not our focus over here. This is something from transmission line theory and microwave circuits. So go through Podzar. More detail is given there. So this is all about what happens if the length of the transmission line is altered and irrespective of the load impedance. There could be another condition where we are joining this transmission line with another transmission line. So in that case, some of the waves will be transmitted, some of it will be reflected. And in that case, we give the reflection coefficient, use the reflection coefficient for the wave which was reflected and transmission coefficient for the wave which was transmitted. And the reflection coefficient in this case, for example, if this was Z0 and this was Z1, Z1, this will be given by Z1 minus Z0 by Z1 plus Z0. We just treat the characteristic impedance of the next line as the load impedance at this point, and we get the reflection coefficient expression. And okay, so this was what I was trying to draw. We have some reflected wave, we have some transmitted wave, we have the total wave which was propagating, we have this transmission injunction over here. This is Z0, this is Z1. Now, for voltage in Z less than 0, so before the 0 mark, the voltage expression is given as what we have already seen, the incident voltage and the reflected voltage over here. And for terms greater than 0, for the next transmission line with characteristics impedance Z1, it will be given by the transmission coefficient as the whatever the incident voltage multiplied by the transmission coefficient is the transmitted wave for Z greater than 0. And so the transmission coefficient is represented by T, and now there's this relationship which exists. T is equals to 1 plus gamma, and we can substitute the value of gamma over here to get the expression for transmission coefficient. So this is all standard textbook stuff. Need not worry. Just go through them. And so this is important way. So whatever is the wave which was transmitted to the next transmission line. Uh, yeah, so the transmission coefficient between 2 points in a circuit is often expressed in dB as the insertion loss. So if you put the if you use this expression transmission coefficient and you take the log, we refer to this as the insertion loss, as the amount of wave which was transmitted through the structure. So there was some incident wave over here, something was transmitted, and you can use this ratio to give the insertion loss. So we talked about return loss, we talked about insertion loss. Yeah, so this is where we end. So this is all we needed to revise before beginning this course. There are more stuff in Podzar. I'll recommend going through the entire first and second chapter from Podzar. Um, but this is all we'll cover in this class. And I've attached this assignment as well. This is pretty much straightforward. This is just some simple numerical. The first question uh, asks you to demonstrate the similarities between the wave propagation wave equations using V and I and E and H from the Maxwell's equations. So if you have to give the relation and give an analogy between the wave characteristics. So this will have R, L, G, C components, and this will have mu and epsilon values. Yeah. So try to write this down. I think solutions might be available in Cheng, DK Cheng. And I'm not sure where I got this question from, but yeah, this could be either from Cheng or Polzar. I'll share the solution as well, but I'll recommend trying this out. So this is all from this class. The next class will start with the introduction to CM and FDTD. So I'll just stop over here um, and wait for any questions you have regarding the material which we covered today, um, or any other questions you might have regarding the classes.
Hello, sir. I have one query, sir.
Yes.
Hello.
Yes, I can hear you. Continue.
Yes, sir. So, sir, while we are modeling the distributed transmission line or maybe distributed circuit in terms of lump circuit, let's say we have a distributed circuit of 1 meter, and now we try to model this distributed element in a lumped element model. So we zoom in the 1 meter line, and we come to a differential element, and then we see the differential R, L, and G and C, those self parameters.
Yes.
But in this model, if we zoom out, we'll see multiple lattices of this this component, this RLGCs, multiple RLGCs stacked one after another.
Yes.
So, but when we are analyzing the individual the single elements, that is the single RLGC, and we are arriving at some differential equation, we are only considering the self R, self L, self G and C. We are not considering the mutual inductances and the mutual capacitances.
Okay.
So when we are then solving the partial differential equation, we get the general steady state solution, which is valid for the whole 1 meter distributed element.
Okay.
So, but we didn't consider the mutual inductances or mutual capacitances. So, so this model, and so viewing a distributed element as a in this model, how accurate is this, and
Okay.
what should we? Yes, sir.
Yes, continue.
Yes, means the how accurate is this way of modeling, and what should we be looking? Means keep looking when we are dealing with this kind of models when dealing with distributed elements.
Okay, so I I'll try to maybe I'm not sure if I have the right answer for your question, but maybe this is what you're trying to ask is like we have a, for example, this huge transmission line, and then we zoom in for this differential section, and over here we consider the RL DC value, and then similarly we will have another section and another section over here, and each of them will have their own RLGC values, and we are ignoring the mutual effects of the next each line. This is something you asked, right?
Exactly, sir. Exactly. And that differential equation is only valid in that differential element only. But when you're solving the equation, that is valid for the whole transmission line. So, how much accurate is this? And that is exactly, sir. That is my question.
Okay, so I don't think I have a good answer to this. Maybe I'll go through with this, but but about the accuracy is something which I can tell you is uh, right now I've not encountered any problems considering just the telegrapher's equations throughout the transmission line. The results which I simulated have seemed to match the measured results. So I'm not sure about how this affects. There, it could be one thing that there might we might not need to look at the mutual components because we are zooming in the same element. Like this, we had this transmission line, right? So treating this section and treating this section separately as two different things might not be the way we should look at. So hence we don't look at the mutual effects of these two lines because they belong to the same system. But again, I am not sure. I'll have to look at this. So if we don't need to consider the mutual effects of the two cells, we I would say that this is the accurate way. But if we have to consider this, then we might have some effects which I'll have to look about. So I'll right now go with this answer that we probably don't need to see the effects of these two unit cells separately affecting each other because they belong to the same transmission lines and not two different transmission lines. But I'll also say that I'll look into this and get back to you if I have a different answer.
Okay, sir. Thank you. Thank you.
Yeah, that was a very
Hello.
interesting question. I'll probably look into this. Yeah, yes, Surbi.
Yes, sir. Like, if we want to model some, like we have transmission line printed on some substrate, and what we know the length and width of the slot line. So, like, it's a slot antenna kind of. So, it's made of transmission lines, and we are feeding in center feeding. We are giving. So, I want to model the input impedance of these slot lines. So it's printed on some substrate. There is metal on a substrate, and slot is cutted out. So we know the width and length of the slot line. So how to model the input impedance of that slot line, and if the width is varying with the length, so how we get the input impedance?
Okay, this question seems to be too advanced for this class actually. So we are touching very basics of this. So what you're trying to say is that you have a structure which has a slot. There is some metallic patch, then and so this is your metallic patch, and then you have some slot. This is
So
on some
no metallic
substrate.
patch. Just say there is some one slot line. So forget about the substrate, and there is some metal and the slot line is cutted out. So one slot is cutted out. So we can say that it's the transmission line, right? So from metal, if we will cut some part, it will be some slot, right? And we can model it as a transmission line.
Still
Get it?
not sure, but whatever your structure is, let your structure be this box. So you can probably make an equivalent circuit out of this. It could be resistor, inductor, capacitor, combinations of these, and with a combination of in resistor, inductor, capacitor, and it could be more complex than this. Okay, and if you can make an equivalent circuit of whatever your structure is, which will depend upon the slot thickness, slots length, and other parameters. If you're able to make an equivalent circuit, then you can use whatever we go through in this class to model that. But the equivalent circuit is something you'll have to figure out for your structure, for your line structure. And there might be specific papers or books dealing with this. I'm not an expert on slot antenna or waveguide things, so I might not be the best person. So you might have to refer to somebody who can help you out with making this equivalent circuit.
Okay,
But
sir.
whatever your
Thank you.
circuit might be, it can be represented in terms of the inductance, resistance, and capacitance. And given it's just metallic and you can ignore the resistances, and LNC combinations will give you an equivalent circuit, and then you can use that in your codes, which will go through in this class.
Okay, sir. Thank you.
Yeah, you're welcome. Okay, so any more questions? I'll probably wait for some time with the class, let things sink in. If you have questions, you can ask. You can also return your questions to me via email or WhatsApp group. Okay.
Uh, I said just a question. Where will we get the material, the video, and also the solutions to the examples, and also the slides?
Yes, so I'll repeat that. The slides and the slides, I'll just post them now in the WhatsApp group. I hope you are there. Yeah, I think you're there. Yes, Benjamin. So I'll post the slides right now. I'll upload the slides on my website as well so that it remains there. Regarding the video, I'm not yet sure. Either I'll upload them as unlisted videos on YouTube or my MS Stream, Microsoft Stream, which I used it in which I was using previously for other courses. I'll get to decide on that. But I'll upload the videos maybe by tonight. So it will be on one of the streaming platforms, so MS Stream or YouTube. But on YouTube, it will be an unlisted because IEEE does not allow us to make like upload videos on YouTube. And
Okay.
regarding the whatever text files or PDFs, I'll share them in the WhatsApp group. I think the codes I'll upload them in on my website. I think, yeah, or maybe yeah,
All
on my website.
right. Thank you so much.
Yeah,
Thank
you're
you for the
welcome.
course.
Yeah, thanks. You're welcome. Okay. Any more questions about the class logistics, in general, any queries? Okay, then. I'll stop the recording now. Yeah.